Let's look at how could we find tangent lines to our parametric graphs. Well, we can find just oblique tangent lines, and we can also find horizontal tangent lines and vertical tangent lines. If you recall, a horizontal line has a slope of 0. So it kind of makes sense that the derivative of y with respect to t, if that equals to 0, we would have a horizontal tangent line. However, the slope of a vertical line is undefined. So how does that work? Well, this comes from the denominator, and if the denominator is 0, that's undefined. And so we will have a vertical tangent line if our derivative of x with respect to t is equal to 0. Now, I must say that they cannot simultaneously be 0, then we have some problems. I've used a graphing utility to allow us to look at the graph of this parametric function. Do you see any possibilities where we would have a horizontal tangent line? I don't. But do you see any possibilities of a vertical tangent line? I think so. Probably right here. Let's do the calculus and confirm that. Okay, so if I think there is a vertical tangent, then that means that dx dt would have to equal to 0. So let's find dx dt. So that would just be 4t cubed. That's pretty easy. Setting that equal to 0 and solving for t, if I divide both sides by 4, I still get 0. If I take the cube root, I still get 0. Well, that's what the t value is. I want to find the points. That implies an xy coordinate system. Right? So if x is t to the 4th plus 2, x would be 0 to the 4th plus 2, so x is 2. And y is t cubed plus t, so that would be 0 plus 0, which is 0. So we would have a point of vertical tangency at the point 0, 2. And that certainly is confirmed by our graph. But let's go ahead and look at possible horizontal. Doesn't look like our graph gives us any, but let's do the math. So we need to find out we have a horizontal tangent if dy dt is equal to 0. So if I take the derivative, I would get 3t squared plus 1. So if I set that equal to 0, let's see what happens. So I'd subtract 1, I would divide by 3, and at this point if I tried to take the square root, I'm going to get an imaginary number, which I don't want in real function world. So this would tell us that there are no horizontal tangents. And again, that's confirmed by our graph. Let's look at this example. So this is the parametric equations for an ellipse. And if you look at that, it certainly seems like there would be a vertical tangent here, a vertical tangent here, horizontal, horizontal. I don't see any other ones, so let's see if we can find those. Right, so one more time, we have a vertical tangent if dx dt equals to 0. So let's find dx dt. So the derivative of sine is cosine. If I set that equal to 0, dividing by 8, I have to ask myself, when does the cosine of t equal to 0? Well, you should know that from your unit circle, or you could go back and look at your cosine graph over one period, and it would cross the x-axis at pi over 2 and 3 pi over 2. Now keep in mind that that is cyclical, so you have an infinite amount of t values. But I think those will be fine. Right? So let's find the points when t is pi over 2 and 3 pi over 2. Right? So that means when x equals 8 times the sine of pi over 2. Well, what is the sine of pi over 2? Again, you could look at your graph, and the sine of pi over 2 is 1. right? We need the y value, so that would be 4 times the cosine of pi over 2. And we know from the over here that the cosine of pi over 2 is 0. So 1 point of vertical tangency is 8, 0. And I believe that would be right here. Well, what about 3 pi over 2? So we'd have x equals 8 times the sine of 3 pi over 2. Well, the sine of 3 pi over 2 is negative 1. So that's going to be negative 8. And then we get the y value, 4 times the cosine of 3 pi over 2. Well, we know that the cosine of 3 pi over 2 is 0. So we have another point of vertical tangency at negative 8, 0. Now again, we do have an infinite amount of t values, and this ellipse would just keep going around and around and around, but you're going to still end up with those 2 points. Now that's vertical. We've got to find horizontal. So that involves dy dt. So how do I take the derivative of cosine? The derivative of cosine is negative sine. So I'm going to set that equal to 0. If I divide by negative 4, I still get 0. So I'm asking myself, when is the sine equal to 0? Again, looking back at your graph, it has an infinite amount of values, but let's just use 0 and pi. We could use 2 pi, negative pi, again, infinite amount. And I believe that's going to give us those 2 horizontal tangents that we see on the graph. Right? So we would have x equals 8 times the sine of 0, and the sine of 0 is 0. And we'd have y equals 4 times the cosine of 0, and the cosine of 0 is 1. So we have the ordered pair 0, 4. Well, 0, 4 is right there. Graph confirms. Okay, let's find that second one. Let's use pi. So we have x equals 8 times the sine of pi, which of course is 0, and y equals 4 times the cosine of pi. Well, the cosine of pi is negative 1, so we're going to get the ordered pair 0, negative 4, which is right there. So that's how you would find points of vertical and horizontal tangents. Well, what about just tangent lines in general? How would we do that? We did that many, many, many times in Cal 1, right? Where you had to find the slope of the tangent line, right? And we needed a point, x and y, and to find an equation of a line, I use my point slope formula. So it looks like I need to find the derivative for my slope, and I need to find an xy coordinate if I want to find an equation of the tangent line when x is equal to negative 2. So let's go, when t equals to negative 2. So let's go ahead and find those x values and y values. So we would have negative 2 to the 5th power minus 4 times negative 2 cubed. Let's see, and that's going to be positive 32. So I've got 0. And I have y equals negative 2 squared, which is 4. So my point would be 0, 4. So the next thing I have to do is, of course, find dy dx. So that's our derivative. Good review. So dy dx is dy dt divided by dx dt. So I want to find the derivative of y with respect to t divided by the derivative of x with respect to t. Now you could reduce out some t's. You can if you want. We could just leave it like that because I'm now going to evaluate it when t is equal to negative 2. So I have 2 times negative 2. Let's see, that's negative 4 over 80 minus 48. So that's negative 4 over 32, which reduces to negative 1/8. So now I have a slope of -1/8. I have a point 0.04, and I'm going to find the equation of that tangent line. So now I can write my equation of my line. So y minus y1 equals my slope times x minus x1. Just going to make that a little bit prettier. And I'm going to go ahead and solve for y. I don't have to. It just looks nicer to have it in that slope-intercept formula. So that would be the equation of the tangent line. So going back to this example that we did a lot of things on a previous video, could I have found an equation of a tangent line given the parameter of t is equal to -1/6? Well, sure. If you look at this mess here, we had gone through and found the derivative when t is -1/6, and so this was my slope of the tangent line, and we found x and y by, of course, putting in our t value there, and we got the xy coordinate here. So could I find the equation of that tangent line? Yes, very easily. So I'd have y minus y1 equals my slope times x minus x1. And again, you could leave it like that. You could clean it up. I think I'm going to just do a little bit more steps. So this would be the square root of 3/2x. If I multiplied that, that's just 3/2. Then I could add 1/2 to both sides. I know I'm squinching this. Square root of 3/2x. And so if I add that, that would be 4/2 plus 2. So finding equations of tangent lines, really pretty easy.